So for an example of how this might play out, we've got a differential equation, pretty standard. You notice this is what we might refer to as a separable differential equation. We could divide both sides by that square root and integrate both sides with respect to t. And we can solve this, right? This is solvable for us. And also recognize that this is, as written, a function of both t and y. So the differential equation is in terms of both the independent and the dependent variable. So the existence and uniqueness theorem asks some important questions. It says, is f of t comma y, is that continuous? And so we look at it, we say, well, yeah, no problem plugging in any value of t, but of course inside that radical we have a bit of a problem. If y is anything below 1, then we have some problems. So we would say to this, yes, as long as y is greater than or equal to 1. Because you can take the square root of 0, but taking the square root of negatives, that gets us into complex number territory, and we're not ready for that yet. So it also asks another important question, is the partial derivative of f with respect to y continuous? And for those of you who may be a little rusty on partial derivatives, all the partial derivative is saying, in this case, take the derivative of this thing, but pretend like anything that's not y is a constant, right? So you see that 4 times t, just treat t like it's a constant. So the partial derivative holds all other variables constant. So when I do that and I take the derivative with respect to y of 4 times t times the square root of y minus 1, you might look at it and think, oh, I'm going to need to use the product rule. But this is just a constant times the square root. So this just becomes the same thing as this thing to the 1/2 power, right? So I can bring the 1/2 out front. It becomes 1/2 times 4 is 2 times t times y minus 1, now to the negative 1/2 power. Right? So the partial derivative of this gives me a function that looks like this. And you might think, okay, is this thing continuous? Well, yeah, no problem with whatever I plug in for t. The only trouble is over here. Now I got to be careful, because if I take the reciprocal square root, I can't have this thing equal 0. So this is continuous as long as y is just greater than, oops, sorry, not greater than 0, greater than 1. Greater than 1. And of course, it's for the same reason this has to be greater than 1, but it can't be equal to 1 down here because it would be 0 in the denominator. So take these two pieces of information taken together, the fact that we have a restriction on continuity, right? As long as y is greater than 1 in this case, just or greater than or equal to up here, and greater than 1 means that tells us that dy dt equals 4t times the square root of t, or sorry, not t, y minus 1. This thing is guaranteed to have a unique solution everywhere that y is greater than 1. Because there's no restrictions on t, so any rectangle that I draw, as long as I draw that rectangle so that it's greater than 1, we should be all set. Or if you want to be more specific, you could say t is everything from negative infinity to positive infinity, and y is everything from 1 to positive infinity, right? Any rectangle that we draw that's fits inside here will meet the bill. And of course, any initial condition in here will have a unique solution. So any condition, notice I emphasize here, it's got to be in this region. We'll have a unique solution. It can't be on the edge, but it can be in, as long as it's in that solution. So what we're going to do now is take a look at a couple of, and we're just going to do this really quickly, a couple of kind of visual representations of what's going on. The sketch down here is a visual representation of the everything's okay region and everything's not okay region. So up in this part of the region, we would say that there are guaranteed solutions. Down here, nope. But notice I say nothing is guaranteed. I don't say that there are no solutions, because I don't know that. The existence and uniqueness theorem only applies up here. So the key for us to remember is, in this region, the existence and uniqueness theorem applies. But once you get down to here, in this region down here, the existence and uniqueness doesn't apply. So in this region down here, the existence and uniqueness theorem does not apply. And of course, right here, right exactly at y equals 1, that's what we would call a boundary. So there's no guarantee. So it's important that we are, careful with our language. When we say the existence and uniqueness theorem applies, that means that we're guaranteed a solution. But down here or in the boundary, we just say, sorry, there's no guarantee. The theorem doesn't apply. So I really can't say anything about it. So down at the bottom it says, so what does the slope field of this thing look like? Well, we can turn our attention to Maple and get a better view of what's going on. So I went ahead and opened up a Maple document, and I typed in the code to come up with a slope field, a DE plot, for our differential equation. And I'm just going to be taking a look in the region right around the origin, so from -5 to +5 on both sides. And that should give us a good view of what's going on. And so when I hit enter on this, we see what we're going to take a look at here. Notice what Maple gives us. Maple gives us a slope field everywhere above the line y equals 1, and below the line y equals 1, it doesn't give us anything. It's as if Maple's saying, look, I have no idea what's going on down there. And so if we try to insert an initial condition here and say, well, what about the initial condition y of 0 equals 0? If we try to do this right at the origin, Maple's probably going to say, look, I can't tell you anything about that solution. And sure enough, Maple says, warning, plot may be incomplete. The following errors were issued. Can't evaluate the solution past the initial point. Problem may be complex, initially singular, or improperly set up. This is Maple's way of saying, look, I can start at 0, 0, but I don't know what to do after that, because the instructions, the differential equation, don't make any sense after 0, 0. So what happens if we change that to y of 0 equals 2, somewhere up here, and see what happens? Maple gives us a solution. Ugh, I forgot about the stupid line color. Can't see it. We wind up with a nice graph. It's a kind of a parabola-looking thing. And it seems to exist, and Maple doesn't have a problem drawing it. But what happens if I change this now to y equals 1? Literally right on the line. Let's see what Maple says. Now, according to the existence and uniqueness theorem, Maple should say, I can't help you, I can't guarantee anything. But notice what it does. It says, well, it looks like the equation, the differential equation, is just going to tell me to hug this horizontal line. Now, you might think, okay, that's great. Maybe that's what the solution looks like. But remember, the existence and uniqueness theorem says we can't guarantee that. Cannot guarantee it. Because if I try something different, like maybe y of 1 equals 2, So y of 1 equals 2. My initial condition right there, I expect a curve that goes up like that and maybe back. But is it going to hit here? Is it going to go horizontal? Is it going to go back up this way on the other side? Well, Maple says, no, it's a curve that looks like this. But here's the trouble. Maple, once it hits that horizontal line of y equals 1, Maple's like, oh, okay, then it just kind of rides along horizontally. But we can't guarantee that solution. So the best we can do is say up to just before y equals 1, it behaves like this curve. And then as soon as we get to y equals 1, everything that's over here, we have no idea how it's behaving. So that allows us to make some predictions. So Maple allows us to see what's going on. And what's really interesting about this is, of course, it says nothing about the slope field lines below y equals 1. So let's go back to the notes and take a look at what's going on the next page. So back on the notes, we're taking a look at the exact same differential equation, but with a specific initial condition. And the thing to keep in mind is the existence and uniqueness theorem says that you've got an initial condition in the region, and that means you can draw a rectangle around it. Right? You can draw a rectangle that contains it, that's in the region where the function and its partial derivative are both continuous. So we say, since we can draw a rectangle around the IC, the initial condition, in the region above y equals 1, which is where all the magic happens for this differential equation, a unique solution. Unique, there we go, I can spell, solution is guaranteed. And so that's good. So in an example like this, if the initial condition's above, then you can draw a rectangle around it, and the solution's guaranteed. The question the theorem asks is, can we draw a rectangle, however small, around a point without going into any of the gray areas, right? The danger zone of there's no guaranteed solution. And so when we drew it in Maple, you saw that sometimes the solution would kind of ride down here, and then Maple sometimes does the and rides it along here. That part of the solution is actually Maple trying to make do as best it can with what it has. But really the solution would look something like this, right? Once you get to the y equals 1, it just kind of like disappears because the solution is no longer guaranteed. So at the top of the next page, we see further example of this. And you'll notice it says, note that the solution doesn't exist everywhere, but it does exist on some interval around the initial value. And so this part of the solution right here is not guaranteed. Because it's at y equals 1. And so Maple, unfortunately, doesn't do us a great service by graphing all this stuff. But if you considered another initial condition, something like this, you can see pretty quickly there's no rectangle that you can draw. And so down here you just say nothing is guaranteed. But notice, we don't say no solutions. We don't say no solutions exist. The best that we can say is no solutions are guaranteed in that region. And you saw the error on Maple. Sometimes there may be a solution, it just could be unreal. It could be something that's complex and that we can't see on a real number line graph, right? We'd have to graph it in terms of the complex numbers, which we don't know how to do. So down at the bottom of this page, there's a little blurb here that's similar to the stuff that we're talking about, which is a quote from a pretty famous philosopher, a fellow by the name of Ludwig Wittgenstein. And he said, whereof one cannot speak, thereof one must remain silent. And that's kind of what the existence and uniqueness theorem is saying. If you can meet all the requirements, then the existence and uniqueness theorem can guarantee. But if you can't meet the requirements, then all you get to do is say, I can't guarantee you anything. The theorem doesn't say anything. So what does the theorem say in this region? Nothing. It is silent. And by silent, we mean it is of no use to us at all. So at the top of the next page, we're kind of finishing off this example. It keeps going and going. If you have something that's on the border or on the boundary, no rectangle can be drawn around it. That means no guarantee. So what does the existence and uniqueness theorem say here? Nothing. Because it's right on the boundary, you can't draw a rectangle. The requirements for the existence and uniqueness theorem are not met. And so Maple, in all of its haste, tries to draw this, and it says, ooh, guys, I think if we were to start with an initial condition right here, it looks like there's a solution. It looks like it's a straight horizontal line. Unfortunately, that's not guaranteed. It turns out y equals 1 is something that we would identify in looking at the differential equation as being what we would call an equilibrium solution. So it turns out that y equals 1 is an equilibrium solution. To the differential equation. Right? But they're not guaranteed, right? So that's an example of a solution that's not guaranteed by the theorem. So unfortunately, we have solutions, but they're not guaranteed to be unique. So that gets us to the end of this little chunk of material.